full subtractor. Full subtractor is a digital circuit to use to calculate the subtraction of three input binary numbers. The full subtractor circuit is complex and it is difficult to implement in compared to half subtractor. Now this is the block diagram of full subtractor circuit, and you can see that we have three inputs A, B and borrow in. So borrow is borrow in, it is nothing but a previous stage borrow which is subtracted from the input given, and we have two outputs, difference D and another is borrow B out. So we can say that A minus B minus borrow in is equal to difference D and borrow B out. Now this is the circuits of full subtractor by using two half adder circuits and one OR gate. Now this half adder circuit 1 is subtract input variable A and B. That means this B is subtracted from A by using this half subtractor circuit once. Now for the next stage, the borrow is subtracted from this output of half adder circuit 1. That's why we are using half adder circuit 2, and its output is the final difference D of the full subtractor circuit. Now the borrow generated by this half adder circuit 1 and half adder circuit 2 are given to the OR gate, and its output is a final borrow of the full subtractor circuits. Now let me see the truth table of the full subtractor circuit. So already I told you there are three inputs, A, B and another, that is a borrow in, and it has two output, difference, final difference D and borrow out. So now the borrow, this borrow is generated during the subtraction of two binary number. Either it may be 0 or 1. So here we are considering all these conditions. So first we make the table, truth table for the full subtractor circuit when borrow is 0. That means there is no borrow occurs during the subtraction of two binary numbers. So and for that there are four possibility of input A and B. So already we have seen either it may be 0 0, 1 0, 0 1 or 1 1. So here this is the first table which includes borrow 0, and when A B is 0, borrow is also 0, we will get difference D 0 as well as borrow out 0. That means there is no borrow occurs. So similarly we can make the truth table. So here this is the final truth table of the full subtract circuit. Now we require two circuits or two outputs, difference D and borrow B out. So for that we can make or implement the actual circuit. Now for this for final difference operation we can design the circuits by using logic gates. So here for the difference operation we are using to get the circuits or the Boolean expression for this difference D output, we are using K map. So here I am taking one K map. Here we are having three inputs A and B. So here I am taking A and another we are taking group of B, C. So there are two input possibility for A, 0 and 1. And what about BC? It may be 0 0, 0 1, and remember this is the third. 1 2 3, 1 0 and fourth is 1 1. Now so you can see gives the please enter the 1 or logic 1 in this K map. So you can see that this first one when it will available when A is 0, A is 1 and B and borrow out is 0. So here A, B and C 0, that means we can write 1 here. Accordingly, you can write, you can put D1 in this table and according to its input. So we will get this table. Now we can write the equation from this table. So from this 1 we can write, that time we require A 1, B, C 0. That's why I am writing B bar, C bar. So our first expression for this one is A, B bar, C bar. Now accordingly to this one A bar, B bar, C. For this one A, B, C. And for this one A bar, B, C bar. Now we can arrange the term A, B, C, A bar, B bar, C plus A bar, B, C bar plus A, B bar, C bar plus A, B, C. Now from these two first terms we take A bar as a common. So here we are taking A bar common in the bracket B bar C plus B C bar. Now this last two term we can take A as a common. So our equation becomes A bracket in the bracket B bar C bar plus B C. Now next this term remaining same. Here we can write equation in this term by using a Boolean expression law. So we can write here BC for this double bar. Double bar eating nothing but BC plus B bar C is common. Now here next A bar in the bracket B bar C plus B into C bar plus A. So you can say that BC double bar plus, here we can write B bar into C bar is equal to B plus C whole bar according to De Morgan's theorem. Now next is equal to A bar, B bar C plus B C bar plus A. Here we can also apply De Morgan theorems. We can write B bar plus C bar whole bar according to De Morgan theorems plus B plus C whole bar. Now next A bar in the bracket B bar C plus B C bar plus A, and we are using De Morgan theorems against. So we can write B bar plus C bar in the bracket into B plus C and whole bar. We can write by using De Morgan's theorems. Now next A bar, B bar plus B bar C plus B C bar plus A. Now we can add this. So this B bar is multiply with this term and as well as C bar also multiply with this term. So we will get B bar B plus B bar C plus B C bar plus C into C bar. So already we have seen that B bar B is and C into C bar is equal to 0. So here our equation becomes A bar B bar C plus B C bar plus A into B bar C plus B C bar whole bar. So you can say that it is nothing but it is A exclusive B exclusive C. So for this difference operation we require one exclusive OR gate of 3 inputs. You can also use 2 inputs, but if you are having 3 inputs OR gate and when you apply this A, B, C input to this exclusive OR gate which provides this output. Now for similarly borrow operation, for that we are also using K map and put this one in this bracket. So you can say that here 1, 1, 1, 1. Now to reduce the Boolean expression or complication, we are making groups, and low is you can make group adjacent one. So here this one and this one makes one group, this one and this one makes one groups, and this one and this one makes one groups. So there are 3 groups are available. Now we can write equation for this group 1. So here you can write this one first. So in this you can say that for that group you will have to require 0 and 1 for A. That's why I am writing A plus A bar. Into here it is BC. Now for second group, for this second group, A bar into B bar C plus BC. Now for this group, A bar BC plus BC bar. Now A plus A bar is equal to 1. So here our BC plus, now multiply this A bar this equation and this A bar to this equation. So we will get A bar B bar C plus A bar BC plus A bar BC plus A bar BC bar. So is equal to BC plus, from these two terms we can take A bar C as a common. So our equation becomes A bar C in the bracket B bar plus B. Now this last two term we can take A bar B as a common. So our equation becomes A bar B into C plus C bar. And already we have seen that B bar plus B or C plus C bar is equal to 1. So our equation becomes BC plus A bar C plus A bar B. So in this equation you can say that 3 AND gates are required. First for multiplication of BC, second is use multiplication for A bar C, plus third AND gate is required for the multiplication of A bar into B, and they are required to the output of this AND gate are added to each other. So for that we have required another 3 input type OR gate which requires which provides the borrow output operation. Circuit of full subtractor. Now here we are using 3 input type exclusive OR gate which provides a final difference of the full subtractor circuit. So here A, B and B in, borrow in, 3 inputs are given to this exclusive OR gate which provides the final difference of the subtractor circuit. Now for borrow we can say that it's required 3 AND gates and 3 AND gates. So here 1, 2 and 3 AND gates are used. We require A bar for 2 AND gates as an input. So for that I am connecting one NOT gate in series with this input A terminal which will provide output A bar. So here this A bar is given to this AND gate, so which makes multiplication with borrow in. So it's provide B into A bar output. Now similarly here we can see that A bar and B outputs are input is given to this AND gate which provide multiplication between A bar into B, and this AND gates provide B and B in multiplication as a output. Now the output of this and 3 AND gates are given to the 3 input type OR gate which provides the multiplication of the addition of these three outputs. It is nothing but it is a final borrow outs. Now next, 4-bit parallel binary adder and subtractor. Now this only one, the 4-bit 4-bit parallel adder and subtractor circuit can be used or can be done by only one circuit. So that means that this circuit is also used as a adder as well as the subtractor. So here there are four full subtractor circuits are used. Now the input A0, B0, A1, B1, A2, B2, A3 and B3. These are the inputs which is required to add or subtract. Now the output is D0, D1, D2, D3 and final borrow out. Now the C in terminal of this first full adder circuit which act as a control input. Now the first borrow generated by this first full adder circuit is given to this second full subtractor circuit, and similarly second is connected to the third and third is connected to the this fourth, and the final borrow out is taken from the fourth full subtractor circuit. Now the exclusive OR gate is used as a gate controller inverter, which is connected to the first C-in of the full subtractor circuit. That means it's controlled. Okay, that means it can be used as a adder and subtractor. Whatever input you have to given, 4-bit input is given, it may be added or subtracted. It is decided by this gate control inverter. So now when the control input, gate control input is 1, that time, it is most important, that time the whatever your subtractor bits, that means B0, B1, B2 and B3, they are this control input or converter, gate converter, it is converted into first complements. So already we have seen that to subtract 2 bits binary numbers, we can use second 2's complement method. So here we are using 2's complement method. So for that already we have seen that whatever your subtracted values or binary number, first it is converted into first complement and then it is added to 1, which becomes 2's complement. So here similarly when control input is 1, so whatever your subtracted bit B0, B1, B2 and B3, they are converted or inverted into first complement. Now the C-in gate 1, the LSB of C-in gets 1 and this 1 is added to this first complement of subtractor bit, which becomes a 2's complement of subtractor bit, and this 2's complement of B0, B1, B2 and B3 are added to the A0, A1, A2 and A3 bit input bit respectively. So we will get the subtraction of B0, B1, B2 and B3 from A0, A1, A2 and A3. Now when the input signal, when the control signal is 0, that means whatever your subtracted bit, it is not inverted by this gate control inverter. That means its value remains same. So whatever your input given B0, B1, B2 and B3 remains same, and this is added to the A0, A1, A2 and A3. That means it is nothing but it can done the addition of 2 bits, or that means addition of B0, B1, B2 and B3 with A0, A1, A2 and A3.